good morning everyone. Okay, so the next segment we are going to talk about is calculating oxidation states. Okay, so oxidation state or oxidation number is of an atom is a form of an what we call electron bookkeeping. So a way of keeping track of the electron movement. Means a way of it's a way you keep track of the electrons movement. Okay, and also represent the charge that an atom will have if all its bonds form were ionic. Okay, or otherwise what we known as ionic approximation. This is pretend. Okay, for example, things like CO2, is definitely a simple molecule. Okay, what you learned earlier is a simple molecule, but you can actually assign charges to like this C down here is actually +4, the O down here is actually -2. Okay, later I'll help you to see why it's +4 -2. Okay, so this part a bit conflict with what you learned earlier in chemical bonding. This is approximate, pretend. Okay, pretend is a ion. Okay, pretend. Okay, so usually the more metallic element is assigned a positive charge. Okay, as you know, metallic usually there's a meaning to it in terms of electrons. It's basically element with the tendency to lose electrons. Okay, of course, I hope you still know how to see the metal alright, on your periodic table. Okay, so usually the element is assigned a positive charge. Okay, if it's more metallic. Okay, electropositive also actually points to the same thing, tendency to lose electrons. And when it's less metallic, it's assigned a negative charge. Okay, normally. Okay, less metallic, negative charge. More metallic, positive charge. Metallic because tendency to lose electron. Okay, then non-metals means tendency to gain electrons. A tendency to gain electrons. Okay, so basically I think earlier on when you draw polyatomic ion, you come across the FO or N, because they are the most non-metallic, so that's why they have the highest tendency to gain electrons. Okay, alright. Okay, so there are some rules, okay, to follow when we assign this oxidation state. Okay, so basically element, okay, is an element regardless how many atoms are. Okay, element, okay, regardless, okay, how many atoms, so long as it's an element, okay, the oxidation state will be 0. Okay, so individual atoms, okay, or otherwise molecules is all the same. All right. Things like S8 even, the oxidation state will be 0. Okay, things like Zn, zinc itself, okay, Mg, okay, the oxidation state will all be 0 so long as it's an element. Okay, so every time you see element is very easy. Straight away you can assign the oxidation state as 0. Okay, then the sum of the oxidation numbers, or what you call the oxidation state, of all the atoms in an uncharged compound is 0. Okay, uncharged compound is 0. Sum of all the oxidation state is 0. Okay, whereas for polyatomic ions, the sum of the oxidation numbers is equals to its charge. Okay, so if the compound is ionic, you split the formula unit into the various ions first, alright? Okay, wait, maybe I talk about rule number two first. Oxidation. Okay, so basically, alright. I think another important rule I need first before talking about this rule is this one. Okay, point number four. Okay, there are certain elements that you can allocate the oxidation state first without, even any calculation. Okay, sorry. Anyway, this I miss group 1, 2, and 13. Let me change it. Group 1, group 2, group 13. Okay, so your fluorine is always -1. Oxygen most of the time -2, unless we are talking about a peroxide. Peroxide is O22 minus. Okay, so the oxidation state of O it's actually each one we're talking about per atom. Oxidation state is always talked about like on a per atom basis. That means one atom is -1. Okay, your superoxide is O2 minus, so the oxidation state is actually -0. Quite weird seldom come across this though. Alright, just let you know. Then hydrogen is a bit special. Most of the time it's +1 when it is with a metal. Okay, sorry, with a non-metal one I'm talking. A non-metal okay. And then it's -1 when with a metal. Okay, so that leads me to this point. -1. Okay, we use a different color. Okay, when it's with a metal. Okay, we call it a hydride anyway. It's called a hydride. H minus. Okay, so the oxidation state is actually -1 in this case. Yeah. Then of course group 1 is always +1, group 2 +2, group 13. Okay, then you might wonder those like group 16, group 17. Like normally 16 we put as -2, 17 we put as -1. But those are not the rest all you need to calculate. Alright, okay? So you cannot assume group 16 all -2. That's the thing. Alright, okay? You can only allocate all this that is in this table. The rest you have to calculate. In a way good less things to memorize. Alright. Okay, so if a compound is ionic, then sometimes it's better to split. Okay, but anyway, let me do some demonstration of how I use rule 2 and 4. Okay. Okay, maybe this one. Okay, oxidation state of sum of the oxidation state of all atoms in an uncharged compound is 0. Okay, let's see. I give you an example like CO2. Okay, so the O normally each oxidation state is -2. Then for the C, actually you don't know. You got to calculate most of the time. Okay, so X. Okay, let oxidation state be X. Then you have 2 oxygen atom. Each one is -2. Overall is an uncharged compound, so it's 0. Okay, that's how you use this rule. So X -4 equals to 0. X will be equals to +4. So oxidation state of C is actually +4. Okay, or maybe another one I can give you is maybe like ammonia ammonia. Give you another example is ammonia, NH3. So the H here is with a non-metal, right? So it's actually +1. There's 3 of them. Okay, so oxidation state of N, okay, let it be X. So I got 3 hydrogen, each one +1, overall equals to 0. So X plus 3 equals to 0. X equals to -3. Alright. Okay, so that's how you use this rule. Okay, then now we look at the green one. Okay, green one. Maybe I can change like a color pen. Okay, that's green pen now. Okay, so this one oxidation state of all the atoms in a polyatomic ion. Okay, take for example, okay, I give you sulfate Okay, SO4 2 minus okay. So let's say you want the oxidation state of S, you don't know. Okay, but you know for the oxygen, right, based on this is -2 okay. So oxygen is -2 Okay, so you have X. Okay, wait I'm gonna X that one. Okay, so you have X plus 4 oxygen, each one minus 2. Then the overall charge is minus 2. Okay, that's what I mean by sum of all the oxidation state is equals to its charge for polyatomic ion. Okay, so the X minus 8 equals to minus 2. So X equals to plus 8 minus 2. So the oxidation state of S is actually plus 6. Okay, not minus 2. So you can see why the rest all need to calculate. Yeah, alright. Then sometimes if it's ionic, it's easier lah. If you go and split it into the ions to take a look at it. Okay, there are certain situation this particular rule is quite useful. Okay, let's go to the examples. Okay, the first 8 also I think is quite simple. Okay, so basically you find the oxidation state of all the underlying elements. Okay, oxidation state of all the underlying elements. I think the last 4 is the tougher ones. Okay, the last 4 is the tougher one. Okay, so this one is quite easy, shown as so you like oxidation state of the NBX, then there's 3 hydrogen. So hydrogen normally is plus 1, right? Down here, normally plus 1 when with a non-metal. Okay, N is a non-metal, so each one is plus 1. Overall equals to 0. Okay, by the way, if it's positive, you need to write the plus for oxidation state. So X plus 3 equals to 0. X equals to minus 3. So the oxidation state is actually minus 3. Okay, and do a couple more. So down here, the O, each one is minus 2. There's 2 of them. So I will like oxidation state of the N be X. Then you plus 2 oxygen, each one minus 2 equals to 0. That's how you do this. So X minus 4 equals to 0. So X equals to plus 4. Okay, so maybe this one I won't go about doing every single thing. Okay, but maybe just show you a couple examples here and there. They allow you practice the rest. Okay, so okay, maybe the next one I look at is this one. Okay, so the Na, because it's group 1, right? Group 1 down here is always plus 1. Then the O is always minus 2. Okay, these are the one I can pre-assign. So this is plus 1. Okay, then this one, the oxygen is minus 2. Okay, so I got 2 sodium, each one plus 1, plus X, then plus 4, each one minus 2 equals to 0. Okay, then I work out what's the X value. Okay, so plus 2 plus X minus 8 equals to 0. So X minus 6 equals to 0. Your X equals to plus 6. Okay, then the next one is I think a hydrogen peroxide case. Okay, so the hydrogen down here is plus 1 because why? With non-metal is plus 1. Okay, so 2 plus 1 plus 2x equals to 0. So 2x plus 2 equals to 0. 2x equals to minus 2. X equals to minus 1. Yeah. Alright, okay, then you go and try the rest. Okay. Maybe I show you just another one. Like this one, hydrogen is plus 1. Okay, because with non-metal, so X plus 4. Overall is 0. Okay. So so this one, the X plus 4 equals to 0. X will be equals to -4. So oxidation state of C down here is -4. Okay, then the remaining 1, 2, 3, I think you go and try. Okay, I won't go through every single thing. Okay, then I go through the last row lah. So in my opinion, it's actually the tougher ones. Yeah, right. Especially this one. This one I think is the toughest. Okay, so the next one this one the Mn okay, so potassium is +1 because group 1 group 1 can pre-assign, you see. Okay, oxygen is -2, so I got +1 plus X because for then I got 4 oxygen, each one -2, overall equals to 0 so +1 plus X -8 equals to 0. So X -7 equals to 0, X equals to +7. Okay, so this is your potassium permanganate. Okay, very famous oxidizing agent. Alright, so we're going to do some titration with it as well. Okay, the next one. Okay, the calcium is group 2 so it's always +2 Oxygen, actually there's 4 of them if you look carefully and then bromide there's 2 of them. Okay, so each one is -2. Okay, so what we do here is this way so you have +2 plus 2X because there's 2 bromine, then +4 because got 4 oxygen, each one is -2, overall equals to 0. Alright, okay, let me work this out 2x minus 6 equals to 0, 2x equals to +6, x equals to +3. Alright, okay, so x is +3 each of the bromide is +3. Okay, next one is the toughest one I feel in the last row. Okay, because the sulfur you don't know, I cannot just pre-assign as -2. Okay, what's going to happen is this okay, I'm going to like let's say like entire M equals to VO2 because I want to work out the charges of the VO2 first. Okay, so this thing you can look at is M2SO4 first. Okay, so if you ask me what's the charges okay, of M okay, M, if you look, this one I did a bit more space okay, maybe I do by the side first okay, you look at it as M2SO4 okay, so if you do the reverse, SO4 is 2 minus M is plus. Okay, so this is VO2 plus. Okay, then you have V okay, so this one is VO2 plus basically the charge of this polyatomic. Then you like the oxidation side of V vanadium. There's this element with chemical symbol V it's called vanadium in case you don't know. Okay, yeah, vanadium now here V either you thought it's some imaginary element but it's not. Okay, so it's X plus 2 oxygen, each one is -2, overall equals to +1. Okay, so X I'm using rule number 3 this one down here, speed up one, easier to do in this case because the oxidation state of S you don't really know. So X minus 4 equals to +1, X equals to +5 in this case. Right, okay, very special And the last one is what we call a lithium aluminium hydride. Okay, so hydrogen is -1. Okay, hydrogen is -1 in this case. Okay, your lithium group 1 is +1. Okay, aluminium, let's find out, should be +3 anyway. Plus X, then you have 4 hydrogen, that's a hydride okay, because it's with a metal, that's why now is -1. Yeah, okay, with metal is -1 okay, notice this one hydride. Okay, so your +1 plus X minus 4 equals to 0, X minus 3 equals to 0, X equals to +3. Okay, so X is +3 can. Okay, so the rest I'll leave you to work it out. The rest is quite easy. Okay, so now I'm going to show you how actually you do this oxidation state explanation. Okay, very very important now. Okay, this one hard shit. Maybe put three hard, very important. Okay, because why? Probably like 90% of the time they're asking you to explain redox in terms of this definition. So you got to be very familiar with this. Okay, then I'm gonna tell you a bit like which are the areas I will look out for, meaning to say which are the area you can get penalized if you don't follow the format for explanation. Okay, so very very important that you know what to do for this part okay, very important okay. Okay, okay, so this one very important maybe I'll show two examples down here, okay, just to get you familiarized. Then the last one you try yourself before you attempt assignment 7A. Okay, I think only after this then you can do assignment 7A. Apologies, should be these two. After these two videos then you can do assignment 7A. Okay, sorry. Earlier video I said you can do 7A, but actually no, must finish this video then you can do. Okay, page 1 to 5. Okay, let's take a look. Okay, so once again this is metal displacement. So this is we're going to assign oxidation state first. Okay, so zinc is 0. Then this zinc because you know sulfate is SO4 2 minus so that zinc has to be 2 plus okay, it's always 2 plus for zinc, very special case although it's not in group 2. Okay, then your copper, same thing down here okay, if you look at it, is Cu2 plus SO4 2 minus. This is copper 2 sulfate that you're quite familiar with we deal with a lot of this in acid bases salt. Okay, so this is plus 2, this is an element, so it's 0. Okay, so now what you can see is that this one okay is reduced, right? Okay, decrease in oxidation state means you reduce. Okay, if you look back down here okay, decrease in oxidation state is reduced, increase in oxidation state is oxidized. Okay, okay, so now this one down here what you can see is that oh no, wrongly. Okay, this one. Okay, this one is increase in oxidation state, so it's oxidized. All right. Okay. Okay, so first thing you have to do is okay, write down which reactant is oxidized okay to which product. Okay, put down the formulas can we okay, but if the reactant happens to be a compound, that means more than one element, then you have to refer to which element. Okay, like the next example. Okay, but down here I think no. Oh yeah, have actually have. Okay, okay, so it's oxidized to which product? As oxidation state of, okay, then down here you indicate the chemical symbol of the element. Okay, like say the first one is Zn, then put Zn. Okay, oxidize, so we say increases from, okay, then the blank here, the blank is for you to put in the oxidation state. We should calculate and then you put in the formula of the reactant. Okay, to which oxidation state in which product. Okay, then of course the next one is about the reduced part okay, so we will say this one okay, so this one you refer to the element because it's CuSO4 okay, then you put in the reactant CuSO4 okay is reduced to which product okay as oxidation state of which element Okay, so reduce is decreases from some kind of oxidation state in some kind of reactant okay, to the oxidation state in the product. Okay, now next thing we are going to do is fill in all the blanks, of course. Alright, okay. So the oxidized one is the Zn. I hope you'll be able to see to ZnSO4 as oxidation state of Zn increases from 0 in Zn to +2 in ZnSO4. Okay, then the next one is your Cu in CuSO4 because CuSO4 got Cu, got S, got O, so I need to make reference to which element important this one. Okay, don't think it's not important you brush it off okay, must take note this part. Okay, if it's a compound, must refer to the element. Okay, so if your reactant is compound need to refer to which element by doing this alright, Cambridge specifically mentioned that, so you need to do that. Okay, alright, next thing is reduce Cu in SO4 is reduced to Cu as oxidation state of Cu. Okay, the element put in the chemical symbol of the element decreases from 0 in CuSO4. Okay, wait, I put wrongly to +2 in CuSO4 to 0 in Cu. Okay, then of course the last part not much space you can put in as oxidation and reduction occur simultaneously, reaction is a redox. Okay, can because like run out of space next time I must give more lines. Okay, then let's look at the next one so you still need the conclusion this part as oxidation, okay, and reduction occur simultaneously, reaction is redox. Okay, so put in the conclusion okay, although it's merely a formality. Okay, let's look at the next one. Okay, that's a final example then I will end this video. Okay, so this one element just now remember we mentioned rule number 1, regardless how many atoms, okay, as long as it's an element, oxidation state is 0. Okay, so this is 0 this is also 0 because also an element, right? Okay, then down here I have potassium group 1, that's +1, iodide is -1. Okay, so immediately I think if you are sharp you'll notice that this one oxidation state increase, right? -1 to 0, so it's actually an oxidized process oxidation okay, then next one is here is -1, here is +1, so this one is reduced okay, so one is reduced, one is oxidized. Okay, okay, let's see okay, so as in Cl2 to KCl okay, is reduced. Okay, so same format. Okay, the oxidized part. Okay, so talk about the element because it's a compound in which reactant. Okay, the bracket part is to guide you you don't really have to write like this, like what I have written in the first example. Okay, so maybe I erase a bit so that you know okay, this way is oxidized to which product, so you follow the template in the first example as oxidation state. Yeah, remove those bracket, refer to the first one, okay, of which element increases from, this part is the oxidation state in which reactant to the oxidation state in which product. Okay, so follow the first example for the template. Then next thing is the Cl2 part is reduce, okay, to which product, okay, as oxidation state of whichever element decreases from whichever oxidation state in whichever reactant to whichever oxidation state in which product. Okay, so now I'll fill in your I in Ki is oxidized to I2 as oxidation state of I increases from -1 in Ki to 0 in I2. Okay, then your Cl2 is reduced to KCl as oxidation state of Cl decreases from 0 in Cl2 to -1 in KCl. Okay, then the conclusion, since oxidation and reduction occur simultaneously, reaction is a redox. Okay, so yeah, okay, I'll stop here for this video. Okay, the next one you go and try yourself. Okay, then due on the 6th of November. So assignment 7A. Okay, I'll cover the remaining examples here. Then I'll go through assignment 7A. 31 next Thursday. Okay, meaning to say it's next Thursday. Right. Okay, so I'll stop the video here.